I'm going to present some work on the use of conditional couples for some astrophysicists, some astronomical data. So the idea of a coupler is, so a coupler is a representation of a multivariate distribution, and it's a particularly interesting representation because it's a function that takes value from the marginal distributions. So you can separate the estimation process of the marginal distributions and the dependent structure among the variables. In particular, you may be interested in some functional of the dependent structure. For example, the Spearman-Rho, the Kendall-Stowe, or some tail dependence indices, which are low-dimensional functional of the dependent structure. So sometimes you're just interested in low-dimensional numbers to represent the full dependent structure. One of the problems when you use conditional couplers is that while in the unconditional setting, non-parametric estimators of the coupler are consistent, when you go in a conditional setting, the estimators proposed, the non-parametric estimators proposed in the literature are inconsistent. And so there is some bias which are really problem specific and often difficult to quantify. But another problem is that choosing the coupler function for the particular problem at hand is particularly difficult. So these are simulations and these are the relative frequencies of correct selection of the coupler through several methods of model selection. So you can see that correctly selecting the coupler may be particularly challenging. So we would like a non-parametric method of analysis, but so that we can perform inference in a consistent way. We are focusing the estimation problem of the functional of interest and their posterior probabilities instead of the full dependent structure. So instead of using directly the functional of interest, which are usually defined in a compact, we can actually use the transformation of them to encourage normality. If we assume Gaussianity on both this transformation and on the bias we actually compute through inconsistent estimator, we can actually use a Gaussian process. And we have proposed a method to do that in a quickly way, in particular in high-dimensional situations. However, the assumption of normality may be too strict in many contexts. And so we would like a fully non-parametric approach to implement in this situation. So instead of making an assumption on the distribution of the transformation of the functional of dependence, we can actually use a linearization of the dependence with respect to a covariate, for example, with a Taylor expansions, but we can also use splines, for example, and then make inference on the coefficients of this linearization. And so we can actually use, for example, empirical likelihoods to approximate the likelihood of these coefficients and then combine them with some prior distributions. So in the end, what we obtain is a set of coefficients of this linearized model and a set of weights representing an approximation of the posterior distribution. We applied this method to a particular situation of data from the Cherenkov-Gamow telescope, which is a telescope observing high energy gamma rays. So the idea is when an event occurs, this telescope is able to see that, and it transforms what it sees into images of this type, where you can see this type of red ellipses, which represent the event, or the gamma rays coming from the event. So the goal of this statistical analysis is to understand if these images are actually related to gamma signals or to other type of cosmic rays. And there are several measurements on these ellipses you can have, so that you can understand if they're actually from a gamma ray. In particular, we are focused on the length of the major axis and some type of another measurement associated with the third moment of this length. The interesting part of this data is that you can have the type of relationship between these variables associated with these ellipses are particularly challenging. For example, if you consider the two variables I said before, you can see that the dependent structure is a very strange form, like this banana-shaped form. And so you would like to understand the dependent structure you can see and to relate and try to model this random destruction through dependence indices. What we do with the approach I've just presented is that actually we are able to define a posterior distribution for the Spearman's rho. And this is the Spearman's rho between, as I said, the length of the major axis and the third moment of it with respect to the size of the ellipsis and the width of the ellipsis. And you can see that in this case, the Spearman's rho seems to have seems to be a function which varies with the covariate in a non-monotonic and non-linear way. So this approach is flexible enough to reduce the number of assumptions we do in terms of distribution and in terms of type of function, but it's still able to reconstruct pretty well this type of relationship. So one of the major point here is that we want to non-parametrically estimate the joint distribution and in particular some functional of the dependence and we want to do that non-parametrically because we don't want to make parametric errors in defining the model. But still, we would like to have a consistent way to do that. And so this method tries to reach this problem. Of course, in terms of implementation, the Gaussian processes can be applied very quickly, but they have an assumption of the distribution. The method based on the empirical likelihood can be slower, in particular because we want weights representing the full posterior distribution. But still, there are some methods that are pretty high. There are some high performance algorithms to do that. So thank you very much.